SMB, if it's like on your network, it can pretty much be spoken to. Let's go through these plugins. Java. Java was the original target of the 1996 Princeton attack. And man, these guys, they did not forget. They actually worked their ass off, and they built a protection in their applet security layer that had not been broken for 11 years. It was broken like a month and a half ago, but had not been broken for 11 years. However, and this is instructive from watching what goes wrong in security, big, huge security system over here. Little tiny backdoor that went all the way around it. There were two ways of reaching the socket code in Java. One was the applet security interface, which was mostly safe. The other, unfortunately, was something called Live Connect, where directly from JavaScript, you could say, I want to create a Java socket, and it would do it. And it would do it completely independently of this big, huge, expensive security layer that they had built. I hate it when it happens, and it happens more often than you guys know. The problem was, Java's solution for the applet security interface was they are going to download their code. And they're going to know the IP address their code came from. And if it came from 1.2.3.4, they are only making connections to 1.2.3.4. Doesn't matter what DNS said, they loaded the code from an address, that's where they're creating socket connections to. Great. Unfortunately, when the browser says, give me a socket to this place, they have no idea where the browser got its stuff. Browser could have gotten its stuff from like anywhere in the world. And so it just said, oh, I guess I have to do a DNS lookup. Crap. Luckily, this only worked in Firefox and Safari. Flash. I feel so bad for Adobe. These guys tried so hard to build this entire complex security model, and this bug from 11 years ago just goes tunnels underneath all of it. Yeah, they had the most mature security model in the industry, and rebinding just broke them 83 ways from Sunday. About Java, by the way, Java has fixed their stuff. They pretty much broke the hell out of their stuff, but they fixed it. We'll talk about Flash later. They're trying. I wish that was good enough. So, there are lots of ways of using a rebind, but how do you actually do this in the first place? What does it mean to take an address from 1.2.3.4 and move it to 10.0.0.1? What's going on anyway? Well, there are not just one. Turns out there are 3 ways, and probably more, but we'll just talk about 3 ways of moving an address from out in China to, printer down the hall. The first way is temporal, the second way is spatial, the third way is just ridiculous. First way, temporal modulation. This is the one that everyone's been talking about. Well, by design in DNS, you just get to say, yeah, this record that I'm giving you, it's valid for now. If you need a record later, do another lookup. It might change. Shockingly enough, it might actually change. That's the exact feature we're looking for. DNS specifically supports rebinding. Awesome. So yeah, you basically advertise every time you're hosting a record. You say, yeah, don't cache it. Just ask for a new one each time, and it will. So your host goes get something at one place, and it resolves to China. And it looks up again, and it resolves to printer down the hall. Very, very easy. Now, there are some networks that say, we don't respect low TTLs. We're going to hold on to a record for at least 5 minutes. Because, hackers can't wait 5 minutes. This is why there are 3 methods and not 1. Because I'm like, all right, you guys want to see what kind of trouble you're in? Let's play. DNS is pretty flexible. You can return 2 records at the same time. And you just go ahead and be like, yeah, this server, it is simultaneously in China and down the hall. Wow! Browser's like, I'm going to pick one. And you know what? It totally might pick the wrong one. And you know what you do then? You try again. Works like a charm. I'm not going to go into the whole mechanism of trying again, but in case you're curious, here's how you do it. Now here's where I start having fun. You know, people were trying to use DNS-TTLs as a security technology. Let me tell you, whenever you try to use something that's not a security technology as a security technology, it never ends well. These things were not, they were intended as an optimization, a way of controlling caches. Let's say you do actually have something in cache, and let's say it's sitting around. Is there any way of overwriting something in cache? Well, it turns out there totally is. When you do a DNS lookup, you do not necessarily get back an address. You can, in fact, get an alias, something called a CNAME, a canonical name. If you are allowed to be the resolver for a given name, you are allowed to return CNAMEs as well. You can return these aliases. This is not a bug. This is a feature. This is a core way that DNS works. Let's take a look what happens. We're going to use this tool, dig the, Domain Internet Groper. Fantastic name, really. And we're going to look up the name 1.foo.notmallory.com. Mallory being the custom cryptographic name for like your man in the middle, your bad guy. We know this is safe because it's not Mallory. So we look up 1.foo.notmallory.com, and we get, oh yeah, that's at bar.foo.notmallory.com. And because I'm allowed to tell you, bar.foo.notmallory.com is at 10:00. And now, we look up bar.foo.notmallory.com, and it goes, yeah, 10:00, that's what I got for bar.foo.notmallory. But now immediately after, we're going to look up 2.foo.notmallory.com. Totally different name. But it too is going to return a CNAME for bar.foo.notmallory.com. But now it's going to say it's at 10:01. Even though we had something in cache for bar.foo.notmallory at 10:00, now because of this new record that's been looked up, bar.foo.notmallory.com, yeah, that's moved over to 10:01. It is not hard to overwrite entries that are in cache. There's like a ton of other methods. So let's review. By swapping addresses out from underneath a web browser, we can get arbitrary TCP and even sometimes UDP access to hosts reachable by the client. Well, what can we do with this? Can we play some games, write some crazy JavaScript SQL clients? Oh God, I don't want to do that. I have SQL clients. Can't we just hook them up? Yeah. I was thinking, why don't we just full-on set up a VPN connection to corporate network using nothing but a Lord web browser? Totally easy. Actually, no, it was an utter pain in the ass. Took like 7 programming languages and 6 protocols. Okay, can I just whine here? What is it about web programming? Every time you sneeze, you're in a new programming language. Make up your mind! Really annoying. All right, we got 3 actors in this little dance. We got a browser that has access to internal resources. We got an attacker that wants access to internal resources. And we got a proxy that's got to hook the two together. Well, we're going to start with a proxy, running some software that I wrote. It's called Slurpee. The name will be obvious in like 10 or 15 slides. And a few small people in this room will hate me forever for it. The basic theme of Slurpee is that the attacker is going to connect to the proxy. It's going to manage the appropriate resources in the browser to service the attacker's connections. We do this using what I refer to as a bucket of sockets. The browser is going to connect. It is going to create a unified connection manager for all endpoints they're copying to. AV question, can someone come up and give me internet connectivity? Crap. So a browser is going to connect, create a unified connection manager for all endpoints. I call this a bucket. The bucket is going to poll Slurpee and is going to ask, hey, you have any connections for me? Eventually, the answer is going to be yes. I do, in fact, have connections. And what's going to happen is the bucket is going to open another iframe inside of it. It's called a socket. A socket's like a socket, but it sucks. Seriously, it's really slow. It is this second iframe is hosted actually at a different domain. It's hosted at, say, 10.001 foo.proxydomain.com. This is for a specific reason. I'll explain why later. Now, when I say poll, let's take a look at what's actually happening over HTTP. We have, 10.001, connection 3. We have some sequence numbers. We have, some port data. We have some data that's to be sent to the browser. Yeah, I totally ported TCP to JavaScript. They knew what they were doing. What can I say? So, the browser at this point has found out, hey, I've got some data to send. It is the base64 decoded equivalent of, the 0 block, the 1 block, the 2 block, and the 3 block. Great. Let's go ahead and do something with this. Well, okay, I've got this second level iframe. I've got this socket. What's it going to do? It can't open any sign-a-socket connection by itself. It needs the help of Flash. And I don't know about you, I ain't going ahead and dealing with some huge Flash IDE. There's this great thing. The guy who wrote it is here. He's my hero. It's called HACS. I had to use it just for the name. It's an open source, totally straightforward environment for messing around with Flash APIs without the inconvenience of, actually having the IDE around. Not only do you get all of those goodness, you actually get this really nice layer in which a, HTML document with JavaScript can go ahead and call functions inside of Flash. Given that I need Flash functions to actually send and receive data, this is perfect. So, we're going to have each of our socket iframes open a Flash Swift file compiled by HACS. So, important question, how many DNS requests does it take to get to the center of your corporate network? Well, first what's going to happen is that we're going to retrieve socket.swift from HTTP attacker. And DNS is going to reply, oh yeah, attacker, that's at 6666. Great. Now, because we got to deal with Flash, Adobe, it's got its security policy. It wants to get a socket security policy that says, yes, it is okay to open a socket wherever you like. And this is actually going to also go to XML socket, because they got their own protocol, attacker. And that's also going to say 6666, no problem. But now, we're going to try to create a socket. We're going to try to make a connection. Again, to attacker, same name. Different port, but same name. But we're going to go again, a third time to DNS. And this third time, no, now we're saying it's 10.001. And we end up with the script from the Swift from 6666, the socket policy from 6666, the connection to the printer down the hall. Works great. And if I do actually get net here, I will give you a demo, but unfortunately I don't seem to have Ethernet back here by any way. So, oh well. At this point, the data flows are fairly straightforward. Flash is going to go ahead, get data on a socket. It's going to try to send the data from the Flash movie down into the iframe of the socket. The bucket is going to visit each of the sockets and be like, you have any data, you have any data, you have any data. It's going to aggregate all the data that needs to be sent back to the proxy. It's eventually going to get it, say proxy, all right, this socket's got these bytes to send, this socket's got these bytes to send, this socket's got these bytes to send. Gives it to the proxy. Proxy's like, hey attacker, I got goodies for you. He hands it over to the attacker. Attacker goes ahead, replies with, great, send these bytes over, and it's just the reverse of that. And it's basically at that point a very simple TCP to JSON aggregation layer. Works like a charm. Domains. One of the things I mentioned earlier is that those sockets inside the bucket, they're actually at different domains. There's, say, 10.001 foo.proxyhost.com, 64.81.64.139, foo.proxyhost.com. They're different domains. Why are they allowed to script? Why are they allowed to push up into their parent bucket? Well, it turns out there's a very nice little exception in the same origin policy that says two things under the same subdomain can opt in. They can choose to allow each other to script. Well, we're going to use the same origin policy to defeat the same origin policy. Sweet. So we basically just say that. We say all these child sockets, yeah, if the bucket wants to go ahead, poke inside, pull out some data that it really shouldn't have access to, no problem. That's it.